Okay, the second point, what the other processes. So other processes are what we will call them. The other processes are described by certain mathematical objects. These are called endpoint Green's function, and in absence of additional backgrounds, in absence of any additional backgrounds. So let's see what I mean by this. So since there is no additional backgrounds, we will not consider any insertions which will sit into on the propagator, but we will consider all possible other diagrams with given number of external points, and that given number of external points is n. Those are the different processes. So we will denote it by, so endpoint Green's function will be denoted by Gn x1 x2 to up to xn. That will be our notation. So G2 x1 x2 is nothing but this diagram, x1 x2. Now could we have G3? So G3 x1 x2 x3. Now whatever we have in our theory is like the path integral of this relativistic action. There is no way you can draw a diagram which will have three external points. You cannot connect them by lines like that, and therefore the result is 0. This is 0. Okay. G4 on the other hand exists, and you can write these three topological possibilities. So these are x1, x2, x3, x4, and we follow the same same naming of these points. Like this is x1, x2, x3, x4, x1, x2, x3, x4. There are three diagrams I plan to draw. And the claim is that those are the three topological possibilities. You can connect x1 and x2 and x3 and x4. Once you connect x1 and x2, you cannot connect x1 and x3 because that kind of a mathematical that kind of a diagram does not exist. That kind of a diagram does not exist, and therefore we cannot draw this. The next diagram that we can take is connect x1 and x3, x2 and x4, and that is another topologically inequivalent diagram, because you cannot make a continuous deformation of this diagram and make it look like this. If your names, this is important, if your names are fixed, once you fix the names, this diagram and these diagrams are these two diagrams are topologically inequivalent. So then let me write the names because it is important here. So another possibility is x1, x4 and x3, x2. So basically what you are doing is that you are asking the question to find all possible topological possibilities. You are asking the question, let us start with any one of the 4 points. Before I drew the lines, we had only 4 points and we have named them. This naming is just a convention, it's just a choice. We could have named x1, x2, x3, x4 and any other way, and so that is not important. After you name them, then you pick one and ask the question, where should it go? So if you choose that to be 1, then you could ask, where should it go? And there are 3 possibilities. These 3 possibilities are 3 different topological sectors. It can go to x2, it can go to x3, or it can go to x4. So these are the 3 possibilities. And correspondingly, you have the expression according to the Feynman rules will be given by delta x1 minus x2 delta x3 minus x4. This one is delta x1 minus x3 delta x2 minus x4, and this one will be delta x1 minus x4 and delta x2 minus x3. Similarly, G5 is going to be 0, and you can have G6 and so on, right? So the conclusion from this study that we have is the following. Conclusion is that the worldline theory, as discussed so far, does not admit a self-interaction, what one means. So worldline theory discussed so far does not admit self-interactions. And as a result of that, all Gn with n odd are 0, and Gn G2n, the even ones, are not 0, but these are all disconnected diagrams. These are all disconnected diagrams. So disconnected diagrams represent independent processes. This process, so you can, if you take any process, you can multiply with itself and just change the names. They will be disconnected diagrams. They are just showing independent processes. Okay, they are not interesting. So disconnected diagrams. So this can be always done in any theory. If you manage to get a diagram, then you can create infinite number of disconnected diagrams by repeating the same diagram. So that is why it is not interesting. So it's represent multiple copies of same process. So this disconnected means multiple copies of same process, though it looks like there are different processes. Just because they are topologically inequivalent, they must describe some process, but it is not these are not interesting processes because it's just the multiple copies of the same process. So the only non-trivial component being G2. Okay, so the view that we are going to take is that so this is what the worldline theory described so far describes. I mean, in terms of processes or computations, because we have decided to not look at non-trivial backgrounds, and therefore insertions are not counted. So if you just forget about insertions, then what else the theory can describe are these processes, infinite number of processes, but they are not interesting. They are repetition of the same. Only one process is a non-trivial process, and the rest are just repetitions of that. So what we are going to do now is that in absence of backgrounds, we will define a theory by the set of or the set of complete set of n-point Green's functions. So that is our view. That is how we define a theory. So our view is that this set of Green's functions, n-point Green's functions, for n equal to 0, 1, 2, and so on, defines a theory. I haven't discussed n equal to 0 in my previous discussion. You could do that. I will postpone the more detailed discussion of this 0. So G0 will not have any points, and will not have any external points, and you can actually have that in this current theory. And the diagram is that if you start from X and come back to X, so X is not an external point here. So this this is a diagram with no external points, and and since it's not an external point, it's not fixed. This is the only diagram of this sort that you can draw here, which has no external points. And the Feynman rule would dictate will be k x minus x but then you have to integrate over d4x. So let me write it. So this will be integral d4x k x minus x. The reason for having that integral is that the x is not an external point. So any point you pick to write a propagator from, it has to be integrated, and then the propagator comes back to itself. So therefore x minus x. So it's funny that the argument is 0 because x minus x, and it has an integral d4x. So this does not depend on x, and there is a volume, 4-dimensional volume factor. So now what we are doing now is to look at the diagrams. Because we are trying to understand the classification of theories, we will just look into the diagrams, and according to the rule, Feynman rules, what expressions, what mathematical expressions they are equivalent to. This is the only thing that we are going to look at now. We will not attempt to compute those mathematical expressions. So this is the mathematical expression, which is fine, but we will not attempt to compute it. That discussion will be done separately later on at a more advanced level. Because of these subtleties, these complications, I eliminated G0 in the earlier discussion, but we have to actually keep that, because that is a definition. The full set of GNs is the definition of the theory. Okay, so now with that understanding, the question is that how to get more more non-trivial Green's functions, GNs. So the answer, straightforward, is that introduce interactions. So the answer is introduce interactions. So how does one do that? So here is the procedure for introducing interactions. So first, recognize a set of diagrams to be some primitive diagrams. So the primitive diagrams, of course, must be having the only non-trivial piece in the free theory, which is this propagator. And then, in addition to that, to make GNs more non-trivial looking, more non-trivial results for GN, you introduce an interaction. An interaction means which is not a line, but a vertex. Since this vertex cannot be described using a worldline theory because it is not a line, it is a point where three lines are meeting. It is basically, so the topological property of this point is separate, is different from any other point along this line. So all those points can be any point on the line. We know how to describe using the Feynman rules. Any point on a line in this Feynman diagram, we know how to describe using Feynman rules. It is a path integral, it's given by a path integral, which results into this propagator. But that path integral does not have any answer how to treat this special point, which does not look like a line, but it's a junction of three lines. So, but the point is that it is only a point and it has only that much of capacity to store information. And in this case, it is just a real parameter lambda corresponding to each point. So it's called a primitive vertex. So each vertex corresponds to a particular, there's a strength of the vertex. Each vertex corresponds to a particular strength parameter, which is the coupling parameter lambda. Okay. Then next stage is to sum all possible topologically inequivalent diagrams that can be constituted using these primitive elements. So sum all possible topologically inequivalent diagrams that can be constituted using these primitive elements. So let us now follow through this procedure. G2 x1 x2 is given by, will be given by a diagram which is x1 x2. Then then what is the another diagram, next diagram that you can draw? So you have to connect x1 and x2 but not simply by a single line, and the variations have to be made by making use of this junction. So here is how you can do. So since there will be a junction, so you can put the junction. So there has to be a junction somewhere, okay, because you have introduced junction, and that is how you have decided to make variations. And if you put one junction, then there is no way you can connect them using these primitive elements. So you need at least two junctions here, and that would mean that you connect this junction and then this and this. You can think about it. This is the only way you can calculate. This is the only way you can draw the links such that the entire diagram is constituted using these primitive elements. Okay, so these points are y and z, and so on. Many other diagrams, infinite number of diagrams can be drawn. Just increase the number of, if you increase the number of junctions starting from x1 and x2, you have to go through a higher number of junctions. Then you are making more complicated nets or graphs, and those are those diagrams. And you have to, this problem is topologically well defined. If you give these constraints, then you can draw, you can figure out how many, how many and what are the diagrams that should appear here. Okay. Once you find the diagrams, then you have to write down the corresponding mathematical expression. So this one is just delta x1 minus x2. This one will have, there are two junctions, and therefore there are two factors of lambda. For each junction there is a factor of lambda. There are internal points. Since the internal points cannot remain in your expression, it must be integrated over. So there are internal points which we have seen in G0 case earlier also. So d4y, d4z, and then there's a propagator delta x1 minus y, delta y minus z, but there are two links y minus z, so square, and then delta z minus x2. So that is the expression that we get, Feynman expression that you get. Similarly, let's calculate G3. Of course, the simplest diagram that you can draw, so these are the 3 points, x1, x2, x3, and the simplest is to connect them by the vertex lambda. Okay, and this internal point is y, and then you can have a diagram, a more complicated diagram, which is not by simply using the vertex once, but you use the vertex more than once. And then you can argue that you can, if you have to use vertex, then you need at least 3 vertices, and and you have to connect them this way. So there are 3 internal points, y1, y2, and y3, and many other diagrams. These are some examples that I'm giving you. I'm not discussing the systematics of diagrammatic expansion, but the point that I'm trying to make is that these are there are infinite number of diagrams, and the point that I'm trying to make is that these are topologically well-defined problem. Once you know the number of external points and the number of internal vertices that you should allow, which all possible number of internal vertices, there are diagrams, and all of them will be contributing. And these are when I write these ellipses, that is what I mean. But the point is that when in a particular term you have a fixed number of external points and fixed number of internal vertices, then the classification of the diagrams, topological variants, that's a well-defined problem. There is no ambiguity here. So one exactly knows what is meant by the question that is being posed here. Okay, so there's a well-defined question. So now the Feynman expressions will be integral. There's only one factor of vertex, so integral d4y, lambda integral d4y, then delta x1 minus y, delta x2 minus y and delta x3 minus y. Similarly, here there are three vertices. So lambda cube, d4y1, d4y2, and d4y3. Then you draw the links x1 minus y1 delta x2 minus y2 delta x3 minus y3, and then delta y1 minus y2 delta y2 minus y3 and delta y3 minus y1. That's the expression. Okay. Here's the slide.